Good morning, class. Before we start today's activities, I think I want to spend just a moment going back and kind of clarifying some of the things that I'm hearing from you from some of your past assignments. One of them has to do with the nature of continuous versus discrete situations. Um, and it really comes down to the physical situation that we're dealing with. An example I like to use is if you're ordering buses for a field trip, you don't order 1.2 buses. So if the x-axis is the number of buses you get, you can get one bus, two buses, three buses, four buses, etc. And then the other axis could be the number of students that could sit on the bus. Because that domain is restricted, you're not ordering 1.6 buses, right? Because the domain is restricted, it's a discrete situation. And I think sometimes that what I'm hearing is that students, some of you are saying, well, if the pattern continues, it's continuous. And that makes sense. If I looked at this, 1, 2, 3, 4, 5, 6, I could continue this pattern, right? Then the next x value would be 7, of course, because it's a sequence. So I would just go down and hit I would hit down and hit 7. And then the next value over here would be not 7/3, but 7 divided by 9, right? And then I could go another one down. I could go 7 divided by 27. So each time what I'm doing is I'm putting another factor of 3 in my denominator because I keep dividing by 3. And I could see all of those. And if I zoom in, I could see, more closely what's happening here. It looks at this point at 8 that it's sitting on the axis, but that's just because of the way. Oh, I did not mean to zoom in that way. I meant to zoom in on just the spot. But that's just because of the way that the graph is scaled, that it looks like that. It's touching it. But if I go up, there's definitely some distance between the origin, or this line x equals 0, and this 0.727. So definitely this pattern continues, yet this is not continuous. And the difference is that what's not continuing is the values in between. As I go from 2 to 1, right? It does not continue in this area because I know this is a sequence. Just like if these were school buses, this is the first term, the second term, the third term, the fourth term. So it's discrete because it's not showing me values in between here. Maybe you could think about it like this, like, oh, you're just being so discrete. You're hiding information. I don't know. Maybe that's a bad way to think about this, but a discrete one has this restriction on my domain. So anytime I see a sequence, there's a domain restriction, and I'm just looking at these ordinal values, the first, second, third, fourth, fifth term, and it is not continuous across this domain, right? It jumps. It goes from 2 jumps to 3, from 3 jumps to 4, and it's not all the things in between. Now, if I was to change this situation and talk about it not being a sequence but something else, I could certainly come up with the function, and it would include this curve that would show all these points in between. Same thing with this linear relationship down here, right? This linear relationship, if this is a sequence indeed, right? Even though it continues, clearly this continues, but that's not what makes it continuous versus discrete. The reason why it's discrete is because I'm told this is a sequence, and this is the first term, the second term, the third term, the fourth term. So it necessarily has to be discrete because I'm missing values inside of here. So that's something I wanted to clarify, the difference between discrete versus continuous. Another thing I wanted to clarify is this idea of a sequence generator. So a sequence generator is not just a number, it's an operation and a number. So if I look at this clearly, every single time I go forward, I'm increasing this by 100. But just writing down plus 100 or this plus symbol and 100 is not enough information, because I don't know if you mean multiplying by 100 or dividing by 100 or raising to the 100th power. So those are all very different. So what you want to say is just write the word adding 100. What's the sequence generator for this one? Adding 100. What's the sequence generator right here? I would say multiplying by 1/3, right? So I'm taking 1/3, multiply by a third, multiply by a third. So multiply by 1/3 is a sequence generator for this sequence. That's both an operation, multiplication, and a value. This one sequence generator is adding 100, both an operation, addition, and a value, 100. So make sure you include both, because if you just write plus 100 with the plus symbol, I don't know what you mean. If you wrote the word plus out, plus, I might be inclined to say, well, okay, there, that's an operation, right? I guess plus is an operation addition, but better just write the word addition, adding adding 100, multiplying by one third. So on to section 5.3.1. We're into the final third of chapter 5. The title is What is the Rate of Change Comparing Growth in Tables and Graphs? So far in this chapter, you've looked at several types of sequences and compared linear and exponential growth patterns in situations, tables, and graphs. Okay. In this lesson, you will compare patterns of growth rates to each other. This work will help you write equations for exponential sequences in the very next lesson tomorrow. So patterns of growth. So here are 1, 2, 3 sequences. And you're given a task here. It says represent these sequences on a graph. And it looks like we just had to click this and it's going to open it up for us in Desmos. It says use a different color for each sequence. Although the graph is discrete, connect the points so you can see the pattern more easily. Oh, it is a sequence. Therefore, it is discrete because in a sequence, we are restricting our domain to the natural numbers, those numbers that start at 1, 2, 3, etc. So you can see in Desmos we're all set up here. We've got a place for sequence A, B, and C, and they're using 3 different colors to show those. So the values are here, and just type in the first 4 values for each. And there's a couple discussion points. These are listed in your book as well. It says how do the inputs and outputs T of n of each sequence increase? How do the inputs n and outputs T of n of each sequence increase? Well, the inputs are pretty clear, right? Because it's 1, 2, 3, 4, 1, 2, 3, 4. Inputs are just increasing by 1 each time. How does the sequence grow? Is the rate of change constant or changing? That's an important question. I'm looking forward to seeing your answer for that. By the way, what I expect to see here for this question, for question 83, is I want to see this graph completed for the first 4 values like this. And then in terms of how does each of the sequences grow, is the rate of change constant or changing? How is that the case? And then there's this idea of draw growth triangles to help answer this question. So a growth triangle is it's a slope triangle, right, where we see the rise and the run. And if you look at growth triangles and they're all the same, right, you know that you have constant growth. If the growth triangles are changing, you know that the rate of increase is the rate of increase is increasing, right? So it's like there's a rate of change of your change versus just a rate of change. If we knew a specific term, how would we determine the next term? For example, if we knew the 10th term in any one of these sequences, right? So let's say if I knew the 10th term in B, what would I do to get to the 11th term? And then finally, which family of functions best models each sequence? So for A, B, and C. So those are discussion points. Certainly you can spin up a doc and share it with members in your class. I will remind you that you need to upload your own copy of that doc. When you write down and say, Mr. Roberts, I work with blah, 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 I'm not going to find that. I'm not going to go look for it. If I see nothing attached to your assignment, I give you 0 points and move on. So make sure that you're uploading a copy of the work that you do with everyone else. So again, for 83, I should see in your doc the Desmos representation for each of these sequences and a brief answer for the discussion points that you see right here. Let's go on to 84. 84 says, for each part below, consider how fast each of the sequences in problems 83 is growing by looking at the table and the graphs. Do not make any additional computations. Instead, make conjecture based on the tables and graphs. If n represents the number of years and T of n is the amount of money in your savings account, which account would you want? Sequence A, B, or C? Okay. Would your answer change if you kept the account for many years? So maybe you extended the length of the account. The next thing says, obtain this resource page. You're not going to do that. You're just going to, actually, you can go back to your original Desmos graph, and for part C, you can extend it out to T of 7 in Desmos. One of the things that they're doing here is I like this, and it's kind of confusing at the same time. They say at one point that they are connecting the dots, even though this is completely a discrete situation. Let's see, is it discrete? Maybe. Well, if we're talking about money, it depends on how the compounding for your interest is going. But you will see them, and at some point they're going to acknowledge that we are going to, even though this is a discrete situation, we're going to connect the dots so you can see the pattern a little bit better. So you're going to extend on C the graph and then give me that picture. And then on D it says, based on your extended graph, do you want to change your answer to part B? Why or why not? And then the final question I want you to respond to today is 85. It says, which grows the most? Will an exponential growing banking account eventually contain more money than a linear growing bank account for the same amount of initial savings, no matter how steep the rate of growth of the linear account is? Use the growth triangles on your graph from 5-83. And by the way, I think you can add those once you copy things from Desmos. You can place some growth triangles in Google Docs, and I think it would be nice for you to overlay that on top of your growth triangles to help you explain this. And then how does growth of a sequence like B compare to exponential growth? How does growth of a sequence like B compare to exponential growth? So that's it. Just question 83, 84, 85. I hope it's clear what I'm looking for when I open up your doc and see it. And again, I encourage you to share a doc with people that you're working with in class or at home. But remember, once you're done with the day for the day, save a copy of that, save it to your own Google Drive, and then upload that to attach that version to your assignment so that I see you've done something. This is Mr. Roberts. Look forward to seeing you in class and online. Have a great day.